All right. So as we go through each of these different conic sections, we're going to learn that they all have kind of a special, unique-ish reflective property. So, well, first of all, the reflective property of a circle is not that well, we'll talk about that at the end, or maybe not even at all. Circle does have a reflective property, but it's not very interesting or exciting. Parabola, though, yeah, it's pretty exciting. So if you have a parabola and you rotate it around the axis of symmetry in 3 space, it'll create what's called a paraboloid. So a paraboloid is basically like a 3-dimensional surface, 3-dimensional parabola if you want to think of it like that, okay? So the reflective property of a parabola is, well, let me illustrate it with the Sketchpad file. So this is a parabola. This surface right here is a reflective parabola. Just from, you guys aren't in physics, but this is kind of common sense. If you have light that comes in and hits a surface, and it comes in at an angle of, let's say, 60 degrees, it will reflect off that surface at an angle of 60 degrees. The angle that it comes in is going to be the angle that it comes out, right? So when it hits this parabolic surface, this light source, if a beam of light comes across and hits it, we would need to draw the tangent to that portion of the curve, and then the angle in is equal to the angle out. If you were to draw it, you know kind of how light reflects. You'd probably get it right just by looking at it. So if I emit light from a point source here, it's going to hit the parabolic surface and kind of shoot all over the place, and then it would hit it again, I guess. Not too interesting. And I could put it kind of anywhere and emit the light. But something kind of interesting happens if the light source is really, really far away. Now, ideally, we would want this light source at infinity so that the beams of light are coming in perfectly horizontally. That'll not happen here. They're still coming at an angle, but they're close to being horizontal. So when it hits the parabolic surface, it kind of seems like most of the beams reflect the light kind of to this point right here. It seems like the light is focused at a point that's about right there. And that's why we call it the focus of a... I lost my spot. Crap. Where was it? If we find that spot, and that's the focus, if we put the light at the focal point, then we should see kind of a reverse phenomenon, I guess. So it looks like it might be kind of right there. So let's try to get the light source right at that spot. All right, so if I put the light source at the focal point, then the opposite should happen. The light should hit the parabolic surface and be directed out horizontally. Now that's not perfectly at the focus. I don't know exactly where the focus is. I can actually say show the focus in the directrix. Now I could put the point light source right at that point. Try to get it as accurate as we can so we can see the right phenomenon here. And now it seems like it goes out pretty close to horizontally. In fact, if you go to move the light source to the point, it'll put it right on that point. And now the light should go out perfectly horizontally. So this has some applications, a lot of applications, actually. Think about a spotlight, where you want the light to be kind of concentrated into a beam. So you're going to have a really powerful light source inside the tube of the spotlight. And there'll be some structures out here to stop the light, because when you emit light, it goes all around. But the light that hits the back surface is all going to be directed out in one spot. Headlights. You don't want your headlights to go too far into a horizontal beam. You want them to disperse a little bit, but the back of those is maybe kind of parabolic. I don't know. The one that I really like is the flashlight. If you remember the mag lights that you have nowadays, you know how whenever you turn the head of the flashlight, it changes the width of your beam. So the back of that flashlight, that reflective portion, is a paraboloid. And whenever you get the beam that goes out the most concentrated in a spot is the spot where, whenever you turn the head of the flashlight, what it does is it moves the bulb, closer to the focus and further away from the focus. So when you get that most concentrated beam is whenever that's right at the focus. Anyway. Another application are satellite dishes. If you have you shoot a DirecTV satellite to the space or whatever, and it's not going to see these beams coming at this angle. It's really, really far away. So those beams are going to be going almost perfectly horizontal. They hit the DirecTV dish, which is a paraboloid, and it concentrates all of that energy, all that electromagnetic waves or whatever it is, to that spot right there. And that's where they have the receiver on that dish. Okay. Last example I think about is football games. Why, whenever you have 40,000 fans in the stadium, do you hear the crunching of the pads or the guy doing the cadence or whatever, whenever he's in cadence? I don't know. No, blue 42, hut, whatever. You can hear that guy talking, but even though there's 40,000 fans that are screaming their heads off. If you look on the sidelines, you're going to see a guy holding a clear dish. That dish is going to be a paraboloid, a nice, big, clear paraboloid. He points it out at the field where the sound waves are coming. Now, you get sound waves from everybody in the crowd, but where you point the dish, you're going to get these a more constant, you're going to get more horizontal waves coming in, and it'll be directed right to where, and then at the focal point there, you put the microphone, and you get a much higher intensity of the people out on the field, and not as much of the people screaming all over the place. Now, if you were to take that dish and point it out to the stands and point it to somebody, you'd hear that person talking very, very clearly. Obviously, they would never do that. So those are the reflective properties of parabolas. They have lots of applications. One application is to take a parabola, like you take a parabola and then you make like a tube, a parabolic tube kind of, and then at the focal point, and make it out of tinfoil so it's reflective, and then at the focal point put a little skewer and then put a hot dog on that little thing there and hold out in the sun, and all the heat from the sun will hit that paraboloid, the parabolic surface, and redirect the heat to your hot dog, and it could cook your hot dog. Or I've never done it before, but it sounds interesting. Reflective property of a circle, not very exciting. But the reflective property of a circle is simply, if you emit a point source, light source wave emitter, and you turn on the switch, it's going to hit. It's going to go out. It's going to hit and redirect the waves back at you. That's about it. There is an example of this though in the Houston airport. Have you ever been to that place in the Houston airport where you stand and at that point, and if you look above you, there's basically a sphere above you. So the wall is a sphere, or a portion of a sphere, and then where you're standing on the ground, they probably have it set up so that the center of that sphere is about the average height of a person. And if you stand right at the center of that and you say something, your voice is going to go in all directions, but all of the voice that hits this spot gets directed right back at you, and you hear your echo. So anytime you hear an echo, it's because there's several places that are reflecting your voice back to give you a concentrated, you hear the concentrated thing, at a later time, because it takes time for the sound to come back and forth. So anytime you hear an echo, that's what's kind of happening. And if you have a sphere, it'll cause an echo.